Hello, I welcome you all in this presentation related with the subject fundamentals of the manufacturing processes, and we are talking about the metal working based processes. So, the first process which is very extensively used and very versatile, very high productivity process which is deformation based process, that is a rolling. So, this process is basically used for the reducing the cross sectional area of the metal stock. So, this cross sectional area is used by decreasing the thickness of the metal. So, while width remains almost constant. So, if like say if we see this is the plate before the rolling, then after the rolling its thickness is reduced significantly, like T naught and Tf, like this, T naught and Tf. So, T naught is the initial plate and Tf is the final plate thickness which is achieved after the rolling. So, whenever this is carried out, there is no change, W almost remains constant. So, V naught and Vf in both the cases it remains constant, but there is a significant increase in length. So, these three components will be forming the volume of the metal. So, L naught is the initial length and Lf which will be significantly greater than the L naught. So, whenever rolling is carried out, what we will see, L naught is less than the Lf and T naught is significantly greater than the Tf. So, thickness is reduced and length is increased while width almost remains constant, W naught and Wf. So, this is what is achieved through the rolling. How it is achieved through the rolling, that is what we will try to see. Whenever the rolling is carried out, it helps to reduce the cross section throughout its length. The variation in cross section is not possible in case of the rolling, and whatever is the length of the product being made through the rolling, it has uniform cross section. So, if we consider the case, there are variety of the shapes which can be produced by the rolling, and these are these may be in form of like say a square section, in form of the plates, in form of the T section like this, in form of I section, L section, C sections. So, such kind of numerous simple shapes, oval shape section can be produced easily using the rolling based processes, and likewise there are so many other shapes like hexagonal shape. So, all these cross sections, these are the various cross sections of the plate which can be cross sections of the members or stocks which can be obtained, while these sections will be uniform along the length. So, the variation in cross section is not possible in the products which is achieved through the rolling. So, how it is achieved through the rolling, that is what we will try to analyze. For this purpose, basically the rollers are used. So, we can see the rollers in this way. Say these are the two rollers and this is the plate which is being passed through the rollers, and here it will be reducing the cross sectional area gradually and then it will be passing out this manner. So, here this will be the final thickness and this is the initial thickness T naught and Tf is the final thickness. Since if we take any particular length, unit length and width, since whatever reduction is obtained, that reduction happens in case of the thickness only, while the width of the plate which will be along this along the, if we can see the same thing in the top view also, wherein we can have the rollers in this manner and say the plate entering in the roller like this and then coming out in the same width like this. So, this is the axis of the roller. So, width of the plate before rolling and width of the plate after the rolling both are same, but there is a significant reduction in the thickness. So, width is same, thickness is getting reduced. So, considering the constancy of the volume, so what we will be having here for unit length we will be getting the much greater length of the metal. So, the length will be more, thickness will be less and widths are same, which is achieved. So, if we consider this is the center of the roller and this is the radius r of the roller and this is where the plate is coming out of the rollers. So, entry is taking place at this point and exit is taking place at this point. So, this is the entry point and this is the exit point. An angle formed between these 2 points is called theta, and which is basically the angle of bite. It determines the extent of thickness reduction which will be taking place. So, greater the extent of the reduction in thickness, greater will be the draught which will be achieved during the rolling. So, this angle of the bite also depends upon the condition in which the rolling is being carried out, means it is hot or it is cold, or the surface roughness of the rollers. So, for a smoother surface or for rough surface. So, for a smooth surface low angle of the bite is used, while for the rough surface high angle of the bite is used. The diameter of the rollers, large diameter of the large dia rollers used for the low angle of the bite, while the small dia rollers result in the high angle of bite. So, hot and cold rolling, angle of the bite for cold it is very low, like 3 to 4 degree, but for the hot it is very high, maybe like 24 to 32 degrees also. So, since the angle of bite determines the extent of reduction, which in turn is influenced by the diameter of the rollers, surface roughness of the rollers, and the condition or the temperature of the metal in which rolling is being carried out. So, with regard to that, if we see these are the factors which will be governing the angle of the bite, which can be used, which eventually be determining the extent of the reduction during the rolling. So, this is what is defined as a draft. Draft D is basically the difference in the initial plate thickness to the final plate thickness. So, the maximum draft which can be achieved, maximum draft D max which can be achieved is found a function of the mu square into R, wherein mu is the coefficient of the friction, between the metal and the rollers. So, if the surface roughness is more, the more draft is possible, and if the roller diameter is more, then the more draft is possible. So, the friction coefficient between the metal and the roller surface, and R is the radius of the roller which is being used for the rolling purpose. This will help us to determine the what is the maximum extent of the draft which can be achieved during the rolling. We know that at high temperature the coefficient of the friction increases, which helps in increasing the draft. So, if we see with regard to that, the coefficient of friction mu is found 0.1 for cold working, mu is in the range of the is 0.2 for warm working, and mu is 0.4 to 1.0 for hot working conditions, because at the high temperature the metal gets softened and it forms more grip between the matting surfaces, which in turn increases the friction coefficient. So, basically during the rolling, when the rollers are rotating, so the friction between the roller and the plate surface actually tends to pull it in between the rollers. So, when the metal enters in the rollers, this is where entry of the metal takes between the rollers. So, here it is compressed, and compression leads to the reduction in the thickness of the metal by deforming it plastically. So, here the metal may have the equaxed grain, but when it is deformed plastically after passing through the rollers, here it will be elongating gradually. So, after the deformation it gets elongated significantly like this. So, the elongation after the deformation and equaxed grain before deformation is found. So, this is the case when the two rollers are being used. So, when the material is deformed by the rolling, we will see that the metal entry, the speed of the metal at the time of entry between the rollers is very low, and the speed of the metal between the rollers when at the time when it comes out is high. So, at the exit the speed is high, while when it enters the speed is low. So, if we see in this configuration, here it exits and here it enters. This is the angle of the bite and this is the center. So, his speed is low here and his speed is high, because here the volume of the metal, for a given volume of the metal, this is the thickness, and when it comes out the thickness is significantly less. So, in unit time it comes out with the greater length. So, the speed of the metal in the beginning becomes low and it keeps on increasing until it exits. So, it comes out of the rollers. So, what happens when the metal enters between the rollers? So, initially what we see that the metal pressure builds up in the metal and then it will keep on increasing and then again it will keep on decreasing. So, maximum pressure is found somewhere at the neutral plane here. So, what is this neutral plane? So, what we see that the roller is rotating at the certain speed. So, there is surface speed of the roller and there is some speed of the metal which is entering. So, in the beginning the metal enters, speed of the metal entering is low while the speed of the roller is high at the entry point. So, at entry the metal speed is less and the roller surface speed is high. This while at the end the reverse happens, the metal at exit, metal speed at exit is higher than the roller surface speed. So, there are two things. One, when the metal enters, the speed of the metal with respect to the roller surface is less. When the metal comes out, the speed of the metal with respect to the roller surface is high. In between somewhere the speed of the metal which is entering between the rollers and the speed of the roller surface both are same. So, that plane where it happens, that is called neutral plane. At the neutral plane, the speed of the roller surface and the speed of the metal both becomes equal. So, if we see with regard to with the way by which pressure builds up during the rolling between the rollers onto the metal and how can we calculate the forces acting onto the rollers, torque being consumed, the torque acting on and the power being consumed, that is what can be calculated using some fundamental equations. So, here the rollers, center of the rollers, the plate metal entering and then it is coming out. This is the angle of the bite, this is the angle of the bite this side. So, in both the sides we will see the pressure gradually build up and then it reaches to the maximum level and then it starts decreasing. So, the variation in the pressure build up is seen like this, where it is maximum somewhere at the neutral plane and then it starts decreasing. At that time when the metal comes out of the rollers, it's the pressure is released and the pressure is reduced and this is the angle of the bite. So, in this process of the reduction in the thickness, the initial plate thickness and the final plate thickness, this is used for calculating the true strain on account of the rolling, is calculated using the simple equation, the log of T naught divided by Tf. So, this is the simple equation for calculating the true strain and then average flow stress acting flow stress of the metal under which the metal will be deforming can be calculated using like say sigma f is the flow stress, which can be calculated using the K strength coefficient, strain raised to the power n divide by 1 plus n. N is the strain exponent, and so the K is the strength coefficient. So, this is how the average flow stress can be calculated, and if we have to determine the contact length, that is means this length of the contact between the rollers and the metal, which will be governing the force to be applied for the given flow stress. So, this the length of contact can be obtained using the simple equation. R is the roller radius multiplied by T naught minus Tf square root of this one can be used for calculating the contact length. Then the roller force, or the force acting onto the rollers, or the rolling force, can be obtained from the product of the flow stress multiplied by the contact length multiplied by the width of the plate. So, L is the contact length and W is the width of the plate which is being rolled, and sigma F is the flow stress, and the torque can be calculated, T can be calculated using the equation 0.5 times of the rolling force F into the contact length, and the power for the rolling can be obtained using the simple equation of the 2 pi omega into the rolling force multiplied by L, the contact length. So, these are the equations which can be used for determining the true strain, average flow stress, and the power required for the rolling, the contact length, the force, rolling force, the rolling force, and the torque which will be acting onto the rollers. So, this is how the rolling process can be analyzed with regard to the stress, strain, power, and the torque which will be acting onto the rollers. Now, we will see this kind of this analysis is applicable for the two roller system, but for achieving the higher draft value, the other rolling arrangements are also used. So, when the two rollers like this are used, it is called two high rolling stand. When the three rollers are used like this, in this case it is called three high rolling stand.